Okay, so today we are going to introduce the concept of induction, and we're going to do so by imagining some experiments, and this device will allow us to arrive at the physical principle, the mathematical expression of which we want to derive. So we're going to imagine doing a series of experiments, and here is an electromagnet. And if I turn this knob to the on position, we can turn a magnetic field on. So let's say I turn the knob and I can produce a magnetic field, say that looks like that. And this is B. Okay, so we can turn a green magnetic field on. And what we have here is a little conducting coil. It's a blue coil. And we can attach its ends to a device that measures the current and see whether there's current going through this coil or not. So let's start with some imaginary experiments. So the first thing that we do is that we turn this back to the off position, so there's no magnetic field, and we take the coil and we put it into this region. We take it out, we can move it around. B is equal to 0, and the current that's measured on the red device is equal to 0. So there's no current measured there. Not a very interesting experiment. So now let's take the coil, the conducting coil, and put it into this region and turn the magnetic field on. And what we notice is that as B increases, there's a non-zero current registered going through the coil. Okay, but when B stops increasing, so B is not equal to 0, but it's not increasing, so B is equal to a constant. Then we have the current back to 0. So notice that 1 and 3 are similar. So we have 0 current through the blue coil in cases where the magnetic field is 0 and in cases where the magnetic field is not 0. But the key common factor there is that the magnetic field is not changing. So now let's imagine having a magnetic field that's constant, as in number 3, but we squeeze the coil. So the coil is in here, near in the magnetic field region, and we squeeze the coil. We get some current registering through the coil. Now let's keep our magnetic field as in number 4. It's a constant magnetic field, but we rotate the coil, the conducting coil, and again we notice that the current through the coil is not 0. So let's pull or move the coil away. Okay, so we can pull the coil away from the constant magnetic field. Again, we find that there's a current registering on the ammeter, on the red device that measures current. Now let's put the coil into the constant magnetic field again, and let's turn the B field off. So the magnetic field decreases from its constant value. So this is similar to number 2, but the opposite is happening. The magnetic field is decreasing. Again, we find that a current it registers on the red device. In fact, it's opposite to the direction that it had in number 2. And let's do all of these things faster. So let's say faster implementation of all of these different processes. The non-zero current ends up being larger. Okay, so our goal is, what is the common element in all of these? What's going on? And so the answer is that we want to recognize that it has something to do with magnetic flux. So the magnetic flux through the coil is the integral of the magnetic field over an area. So it could be the area of the coil. And the key issue here is that that's changing. We can change that in different ways. So this is magnetic flux by definition. And what we notice here is that in situations where the magnetic flux changes in time, that leads to a current. So we can change the flux by increasing the value of B or decreasing the value of B, as we do further down. Right, so we change B. We can squeeze or stretch the coil. That changes the area part. Or we can rotate the coil. That changes the dot product. Right, we're rotating the normal to the surface of the coil, and the magnetic field direction, that changes value, and so the dot product changes. So these are essentially the 3 ways in which we can change the magnetic flux. So this is what leads to a current being generated. But now we want to get a sense of what is the mathematical relationship between current and changing magnetic flux. And to do this, we can argue from dimensional analysis. So what are the dimensions of changing magnetic flux? Well, magnetic flux is magnetic field times area, so that's B times area. And we're dividing by dt, that's the time. So dimensionally, the changing magnetic flux is a physical quantity that has dimensions of magnetic field times area divided by time, which we can write as, let's write it as length squared, right? Area is length squared divided by time. And what I want to do is try to bring in magnetic force into this. And so I'm going to construct, I need a speed, so I have B. I'm going to bring in a V. V is an L over T, so one factor of L is used up in here. And so I have another factor of L here. So I have BVL. And I'm just one step away from turning this into magnetic force, right? Because magnetic force is QVB. So let me throw in charge. Right? I have the V and the B. So QVB. I have the L part, and all I did was multiply this by a charge, so I'm going to divide by a charge. So I haven't done anything to the expression, but now notice that this part here, QVB, that's force, that's magnetic force, so I have force times distance over charge, and that's a work that has dimensions of work per unit charge. But work per unit charge is the same thing as the dimensions of electric potential or voltage. So this quantity, the changing magnetic flux, has dimensions of voltage. So we can say that d phi dt is equal to a voltage, and the symbol that we use for this is epsilon, for reasons that we won't go into at this point. But there happens to be a minus sign, and we'll discuss this in a little bit and see practical applications of this. So this is the new idea that we've just imagined discovering from experiments. There is, maybe we can flip this around and write that there is an induced voltage in a coil that depends on the changing magnetic flux, but this voltage, by Ohm's law, is related to the current. So we have current times resistance. Right? This is a version of Ohm's law, V equals IR, but for induced currents.